Hello, I'm Kohei, a PhD at AI Hannover. In this talk, I report the current status of the development of pseudo-random noise ranging and optical data communication for the LISA TR6 demonstrator. LISA is composed of 3 satellites, and satellites in LISA keep moving at the speed of around 10 meters per second. As a result, a board interferometer in LISA has very unequal arm length, which is very sensitive to laser frequency noise coupling. So to suppress this overwhelming coupling of laser frequency noise, we need to synthesize equal arm interferometer in post-processing using technique called time delay interferometry. In this algorithm, we need to shift our phase signal with properly selected time delay, delta t. Question arises here, how do we know delta t? This is exactly absolute ranging. This slide shows how we achieve the ranging. So in LISA, for clock synchronization business, we need to embed our onboard clock to be in phase using EOM. On top, for this ranging business, we need to embed so-called pseudo-random noise code, or just PRN code, also to be in phase using EOM. So what is PRN code? It is just 0-1 digital data, which is carefully designed. So this is embedded to be in phase and propagates to the distant spacecraft. And at the distant spacecraft, this received code is extracted by our phase meter. And the phase meter also is generating the digital copy of the received code, and the phase meter compare the digital copy with the received code to get how misaligned these two in time. So this is exactly the ranging. So this gives us the light travel time between two satellites. So this is how we achieve the pseudo ranges. And I set the phase meter needed to compare two codes, and this means just the computation of correlations between two codes. So this slide gives you some parameters around PRN code. So PRN code has the repetition rate of around 1.2 kilohertz. So this gives us the ranging ambiguity. The one chip in the code has a frequency of 1.25 megahertz. And we can shift or align this code with the resolution of the clock frequency driving phase meter, means 80 megahertz. Or in meter, it corresponds to 3.7 meter. So this gives us the ranging resolution. On the right, I'm showing some example power spectrum of our signal at photoreceiver in LISA. So this is simulation. So in the middle, we have carrier bit node, and we also have side one bit node to extract differential clock signal between two onboard clock. On top, we also have this common-like structure. This is the PRN code contribution. And nominally, we invest only 1% of the carrier power for the PRN code, PRN modulation. So these parameters are not finalized yet, and some adaptations are being considered at our institute to align the PRN codes better with an overall LISA timing architecture. So I explained how we achieve the pseudo ranges. The PRN code transfer has another functionality, which is the data communication between satellites. So downlink is configured with only one of 3 satellites. As a result, 2 other satellites need to transfer their own data to the selected spacecraft. The science data needs to be transferred from 2 spacecraft to the selected one, which is communicating with us on ground. So how the data transfer is achieved? So the answer is science data is encoded on PRN code with XOR operation. So to explain that, this plot shows PRN sequences with and without data encoding. So orange shows the PRN sequence without data, means the digital copy at the receiver side. Green on the bottom just shows the example of 01 science data, which is encoded on the received PRN code. And finally, blue shows the PRN sequence with data encoded by XOR operation. So because of XOR operation, when science data is 1, the PRN sequence is inverted. When the data is 0, there is no inversion. It means by checking the sign of the correlation, we can extract or deduce the encoded data at the receiver side. So this is how we encode and decode the science data. So the current data rate is about 78 kilobits per second, and the requirement of bit error rate is 10 to minus 7. So I explained the two functionalities with PRN code. The one is pseudo-ranges, and the other is optical data communications. So at our institute, we are trying to verify our design with a very simple optical experiment. So I explain it from now on. So what's done here is very simple. We just make interference between received beam, red, and local beam, blue. And the distant onboard clock and the PRN sequence with data is embedded to phase of the received beam. And locally, we also have another independent onboard clock, which is driving phase meter. And this is also embedded to the phase of the local beam. And the interference is measured by photoreceiver and phase meter, and encoded data and the pseudo range can be derived by our phase meter. So this is what we want to test. So let me first show the current status of data communication. So here we just compare, decoded data with the one we encoded, then checked how many bit errors exist. So unfortunately, the performance of bit error rate is not very stable. So x-axis is measurement time and the y-axis is number of bit errors. So in this particular example, there is no bit error, so the perfect, up to around 3000 seconds. But as you see here, we often have this kind of sudden increase of bit errors. So on top, I'm also showing the correlation between the digital copy, local digital copy, and the received code. And at this particular time, there is no glitch or something here, in autocorrelation. This suggests that the loop to extract the data and the pseudo range seems to be stably locked. So currently, we are thinking that there seems to exist some problems with 78 data rate clocking in the loop. So the debug needs to be done. So here I'm showing the current result of the pseudo ranges. So I'm showing the raw pseudo range in orange and the differential clock signal measured via sideband bit node in green. So what's important to know is that the pseudo range is affected also by a clock difference because it is an onboard clock itself which generates a PRN sequence. So to demonstrate it, we smoothed the raw pseudo range with a differential clock signal to get a pure ranging signal shown in blue. So as expected, the raw pseudo range and the differential clock signal match each other very well, and after subtraction, we can get rid of the coupling of the differential clock. So this is what we want to demonstrate it. And here is the same result in the frequency domain. So at the raw frequencies, raw pseudo range nicely show the coupling of the differential clock. And after the smoothing, we end up with this blue line. So this tells us the current noise floor of the pseudo range. So the coupling of the differential clock is well demonstrated with current design, and 1 meter RMS requirement can be constantly met with 78 kilobits per second raw data transfer. So here is summary. So the PRN and optical data transfer is under verification for integration in the LISA TR6 demonstrator. So the current design can constantly reach 1 meter RMS requirement. However, as mentioned, with error rate is not stable, so debug is ongoing. So to wrap up this talk, let me advertise some relevant live talks. Our colleague Esteban is giving current status of the engineering model of phase meter. And again, our colleague Thomas Schwarze is going to summarize the ongoing measurement with the latest version of phase meter at our institute. And I also give the live talk with our optical test bed called Hexagon to verify some phase meter functionality. So currently we are implementing this PRN business in this optical test bed to verify its performance in the optical test bed. So I'm giving the latest update on this optical test bed. Yep. So thank you for watching this talk, and looking forward to seeing you again in our relevant live talks.